Hello everyone, welcome back to Fundamentals of Nano and Quantum Photonics. This is the second week of the course, and in the last week we have seen some basic ideas about electromagnetic waves and dispersion and how waves propagate in a medium. So in this week we would like to understand the interaction of electromagnetic waves with matter in some detail. Okay, so the first scenario we will consider is, let's say there's an electromagnetic wave that is incident on a medium. Okay, I'm just representing this medium by a block here, let's say some thing, and we have a wave incident, and let's say this wave is can be described by E0 exponential okay, we have used in the past ikx minus omega t, right? This is what we are using. So this is the plane wave. What happens? The first thing that you would expect is that there is an impedance mismatch. We know that the free space is defined by an impedance, and then there is an impedance associated with any material, right? Let's say this material can be described in terms of a refractive index, and that refractive index we said should be complex, right? There are two terms, the real part and the imaginary part. Okay, and so the n is refractive index and k is the kappa is the extinction coefficient. So now when wave is incident on this medium, what happens? The first process that could occur is some of the electromagnetic energy will be reflected. So reflection is the first process that can occur. So let's list out the processes. So the first one, reflection. What else can occur? So when we are considering the electromagnetic waves, we have also shown that there is an attenuation of the wave in the medium, and the amount of attenuation is defined by the extinction coefficient kappa. So I'll say second process that can happen is absorption. Just to recap, how does the absorption occur? Well, the electromagnetic wave I can describe, let's say this is propagating in the x direction, I'll say exponential ikx minus omega t, right? This is how I say we can describe the electromagnetic wave. And now the wave vector in the medium is going to be not k0, it's going to be modified by the refractive index. So the wave vector is going to be this k now is going to be, let's say, n tilde omega by c. If there was no medium, then we saw the dispersion relation was omega equal to ck, right? So k will be omega by c, but because of the presence of the medium, we will say that k is n tilde omega c. That essentially means that there is this n complex quantity times omega by c. Now if you put this back into the equation, you will see that the electromagnetic wave will be split into two parts, right? Exponential, the complex part wherein you know n omega by c x minus omega t, this is one part which is actually the oscillating part, and there's an attenuating part which is I and I will cancel out. So I square, I and I into I will become I square minus 1. So minus and minus, so basically it will be minus kappa omega by c times t. Okay, so we saw this already. Sorry, this should not be t, this is x dependence, right? Because kx, we're substituting for k, this should be x. So as a function of x, the wave is attenuating. So this is the electric field. If you look at the intensity is going to be simply E square, complex quantity squared. So that will turn out to be proportional to just the exponential and minus 2 kappa omega by c x. Okay, and this sort of we would relate it to a simplified quantity alpha, where we define an absorption coefficient, which is exponential, we relate it to minus alpha x. So by comparing these two, your absorption coefficient alpha is going to be 2 kappa omega by c, right? So just excuse me. Yeah, so we can even, you know, there's a more widely used form, which is you substitute for omega. Omega is 2 pi by frequency, right? Sorry, 2 pi frequency. So frequency is c by lambda. So that will be the more widely used form is substituting for omega equal to 2 pi nu, 4 pi kappa by lambda. Okay, this is a more widely used form of absorption coefficient. Okay, so we know that, let's say if you have an oscillating wave, the wave is going to attenuate in the medium. The attenuation is captured by this absorption coefficient. All right, and of course, some of the electromagnetic energy can survive provided the absorption coefficient is not too high. Some of the wave will transmit, so that will be the third process that can happen. Transmission. Okay, so I'll call this as T, absorption as A. So these are the three main processes that can occur, and if there are no other effects that are in play, then we will see that R plus T plus A should be 1. So basically the incident amount energy is, let's say 100. Let's say 20% is reflected, 30% is transmitted, and remaining 50% is absorbed. So overall the energy has to be conserved. So R plus T plus A should be equal to 1. All right. So these are the primary processes. Of course, there are a couple of more. For example, if the medium has some scattering centers, okay, the electromagnetic energy can scatter. What do I mean by that? Let's say, it doesn't, let's say even an atom, right? When an energy is incident, the energy can scatter. The efficiency with which it scatters is different. But let's say I consider some sort of an atom in a medium, and then electromagnetic energy is incident on that. Then my energy can go in all different directions after it hits the atom. So it can go in different directions. This process is known as scattering, and this you widely see in the in the sky, right? When you see the sky is blue because you have all these molecules that are present, and light is getting scattered from that, and the scattering efficiency is actually high for blue wavelengths. So you see the sky to be blue. All right. So so this process is a very important thing. So it's a scattering process. If I look at scattering itself, there are two different types of scattering that can occur. One will be called as elastic scattering, and one will be inelastic scattering. So elastic means the energy is not lost. For example, a blue wavelength is hitting a molecule, and it's just the blue is getting scattered. That is elastic scattering. There is no loss of energy. In some scenarios, there could also be loss of energy. For example, I have a blue energy which is incident. It excited some sort of internal vibration modes in a molecule, and then slightly downshifted energy is transmitted. In that case, we call it inelastic. One of the prominent or well-known examples for this is Raman scattering. Okay, so yeah, scattering is one of the phenomena that can occur. And one more phenomena that can occur is called luminescence. Okay, luminescence essentially means that you have a higher energy photon that is incident, and then that will excite certain levels in the material, and then the energy will be re-excited at a slightly lower energy. Okay, so this luminescence process is for example responsible for in the older tube lights, we used to have a phosphor element which was excited by UV radiation, and then that will emit white light, right? So that sort of a process is called as luminescence. Okay, so this is also another important feature. You might wonder, how is luminescence different from scattering? Because scattering, I also said that scattering also can result in a change in energy, right? So how is luminescence different? Well, it turns out that the luminescence is slightly longer lived process, whereas scattering is short. So the time scales over which scattering occurs is in the femtoseconds or time scale, whereas luminescence occurs, the time scales are longer, in the order of nanoseconds. It could be in the order of nanoseconds. All right. So these are the primary ways in which the materials will respond to incoming radiation. All right. Just yeah. How do we even look at that? How do we understand what is happening? So we'll have to do some sort of basic classification, and most of you should be familiar with this broad classification of materials into semiconductors, insulators, and metals. So, but you might have studied about them in terms of the conductivity of the material. For example, semiconductor is a material which has intermediate conductivity between metal and insulator, right? That's something that you might be familiar. But you could also think about it in terms of the interaction with the photons. Okay, so for understanding this, we actually introduce an idea that many of you should be familiar of, the energy band gap. Energy band gap. To understand the semiconductor and insulator response, we need to look at the energy band gap. So let's say I have my energy bands in terms of the valence band and the conduction band, and then a photon is incident on that. What do you expect will happen? Well, the semiconductor will have a certain band gap, which is let's call this as Eg, and let's say if my photon has a lesser energy than the band gap, what do you expect will happen? Let's say if h nu is less than Eg, well, the photon does not have enough energy to excite a carrier from the valence band to the conduction band, so the photon is transmitted. All right. But if h nu is greater than Eg, for example, the energy of the photon is greater than the band gap, then the photon can actually cause an electron to go from the valence band to higher energy level, which is the conduction band. Okay, conduction band has a lot of empty states. Valence band is full of electrons. So this transition can happen. An electron can go from here into this. When this transition happens, the energy is transferred to the electron. Therefore, the photon is lost or photon is absorbed. Right. So in the case of a semiconductor having a semiconductor with band gap of Eg, if a photon is higher than band gap, then photon is absorbed. Okay, so this is exactly what happens, and you can look at the band edge, right? The threshold above which the photon will be absorbed. You can think of in terms of energy, in terms of Eg, or you can think of in terms of wavelength. So I can also define my what we usually call as UV absorption edge, which essentially is lambda, let's say G. I'll just call it associated to the band gap, lambda G. And that will be, we have seen this relation in the past. So 1.24 EV, right, divided by Eg in EV. That will give you the band edge in EV. So this lambda G will be in microns. Okay, if I do this. So for example, I have two materials here, sapphire and cadmium selenide. So if you look at sapphire has a band gap of about 7 EV. Okay, Eg of sapphire is about 7 EV. So the band gap also depends on the orientation and stuff, but let's say approximately 7 EV. And if you have that, my band edge is going to be simply 1.24 divided by 7, and that will turn out to be approximately 0.17 micrometers. Okay, so if you look at the spectrum here, this is a transmission of the through the material, and of some thickness, probably few millimeters, and then the wavelength of various wavelengths, how are they transmitted, and you see that above, or rather above a band gap energy or below this edge, so which is UV, right? So in this part is essentially the UV part of the spectrum, short wavelengths, less than 300 nanometers is usually called as UV. So in the UV part, you see that the absorption is increasing, because of that the transmission is reducing for sapphire. Okay. And in the visible, essentially where 300 to 700 nanometer range, the energy is less than the band gap, so that those photons are transmitted, and that's why you see the absorption to be high for a sapphire substrate. Okay. And you might ask, oh, what's happening in the infrared, the longer wavelengths? Let's say in this case, I think about around 2 micron, we have a dip in transmission, and also above, I think 4 or 5 microns, there's a strong absorption. What is happening here? Well, these are essentially related to what is known as phonon absorption. This dip, and then this energy is rather wavelengths greater than, in this case, 4 microns, we have phonon absorption. Okay, and that's why the transmission dips. In the lower wavelength side, or the higher energy UV side, we have absorption because of the excitation of carriers from valence to conduction band. And if you have in the longer wavelengths, the absorption is because of phonons or lattice vibrations. Phonons are simply, you have the lattice, let's say in this case sapphire, right? It's aluminum oxide, Al2O3. So you have the certain geometry, and then these aluminum and oxygen bonds can actually vibrate, and that vibration is called as a phonon. And because of these vibrations, which are broadband, you can actually have strong absorption. Okay, so this is about sapphire. And similarly, you could also look at cadmium selenide. Cadmium selenide's band gap is, I think, about 1.7. Okay, so the band gap in this case, Eg, is about 1.7 eV. And so if I calculate what is the band edge, you could see that this will turn out to be roughly about 0.7 micrometers, okay, up to 700 nanometers. So now, because of that, you see that this energy is essentially smaller than the, this is my, this is 1, so this should be 700 nanometers here. So this is my 700 nanometers. So below 700 nanometers, it's absorbing everything, okay, whereas above that, it is transmitting. And you see a similar signature of, at the longer wavelength, the phonon absorption is kicking in. You might ask, why is the phonon absorption kicking in at around 11.5 microns in this case of, let's say if I go where it goes to 0, this is 11.5 microns. And this is maybe, 4 microns, about 4 microns, right? In the case of sapphire. Why is the phonon absorption edge different? Well, we will come back and we'll answer that in the subsequent lectures. But for now, yeah, this is a phenomenological description of what is happening in a semiconductor, right? I mean, a more common example that all of you should be aware is glass. Let's say I'm wearing my glasses, right? The glasses are transparent. Glass is nothing but silicon dioxide. So if I look at glass, its band gap, silicon dioxide is about 9 eV. So because it's 9 eV, the edge, right, a UV absorption edge will roughly be around 170 nanometers. So lambda G is going to be roughly 170 nanometers. Okay. So any wavelength longer than 170 is going to be transmitted. So all of the visible light is getting transmitted. That's why I see that my glasses are transparent. Okay. And if I look at a cadmium selenide wafer, I'll see that it's not definitely transparent. Well, I mean, it's not going to be transparent. And your, let's say sapphire has a certain amount of transmission, all right? If you take silicon, silicon's band gap is 1.1 eV. So you'll see that the band, absorption edge is basically 1.1 microns. So all the visible wavelengths will be absorbed by silicon, all right? So these are some simple things that, when we look at these materials, we should think of that. There is an interaction of the electronic and the photonics part of it, okay? There's a lot of effects involved, okay? So this is how semiconductors and insulators behave. Well, what is the difference between a semiconductor and insulator? An insulator is a material with a very large band gap. For example, silicon dioxide, it's an insulator. It has a 9 eV band gap. Sapphire is an insulator because it has 7 eV band gap. Whereas cadmium selenide is going to be a semiconductor. You can actually dope it and try to make it conductive. Or, gallium arsenide is a conductor, is a semiconductor. Okay. So yeah, the extent of the band gap really defines whether it's a semiconductor or an insulator. Gallium nitride is another example where the band gap is 3.4 eV. So that's another semiconductor. But usually above that, we don't really consider them as semiconductors. We call them insulators. Okay. So this is the broad classification. Of course, there's another class which is metals. I'll come back to it in a short while. All right. But let's look at that is the qualitative description. The actual description, if you look at, actual data, if you look at here, this is the absorption of various semiconductors plotted as a function of wavelength. Okay. And you see that, below a wavelength, the absorption band edge, you will see absorption is going high. That qualitatively makes sense. But if you look at it closely, you will see that certain materials, for example, indium phosphide in this case, indium phosphide and gallium arsenide, especially these two, show a very, very steep rise in absorption after the band edge. Gallium arsenide has a band gap of, in terms of wavelength, it will be 870 nanometers. Gallium arsenide should be green here. This is 870 nanometers. And the purple thing is indium phosphide, which should be roughly around 900 nanometers. Okay. So you see that below the wavelength of 870 or around 900, the absorption is increasing steeply. But if you look at silicon, silicon's band edge will be about 1.1 microns. Below 1.1 micron, the absorption is increasing, good, but it's actually going in a very gradual fashion. Okay. Similarly, with this is germanium. Germanium also shows a gradual increase in the absorption. The reason for this is what we will usually call as direct and indirect band gap materials. Okay. This is another concept that I would just, if you're not familiar with the electronics part of it, then just accept it for now. Let's say you can draw what is known as EK relation, wherein basically in a direct band gap semiconductor, the band gap is direct. Okay, we call them as direct band gap semiconductors. Direct band gap. What we mean by that is the peak of the valence band, right? This is the peak of the valence band and the minimum, the conduction band. Okay, CB minimum and VB maximum occur at the same K, a particular K. So practically what it means is that it's much more easy, it's very easy for a photon to be absorbed, provided the energy is higher than the band gap. Okay. This is in contrast to the indirect band gap materials, wherein K and if I draw for an indirect band gap material, I'll have my peak in the valence band and my minimum in the conduction band, but they don't occur at the same K. Okay. There is this difference where the peak and the minimum in of the valence and conduction band respectively occur. And it turns out that this K essentially signifies that for an electron to go from now valence band to the conduction band, it needs this energy, and also it needs an additional momentum that comes from a phonon. So this process is not a very efficient process. Okay. So I don't want to go and explain about what is EK relation, but I mean, there are two ways of depicting energy band diagrams. One is in terms of energy versus momentum. Okay. We introduced that, energy and how is energy and momentum related for an electron. So it's a parabolic dispersion for most materials. So for the materials that you know of, let's say silicon and germanium and gallium arsenide and so on. So in that, you see that this kind of a parabolic dispersion will come in, and depending on where the peak and the minimum of the valence and conduction bands are, we can classify materials as direct and indirect band gap semiconductors. So due to that, you see that this germanium, silicon, and even very, gallium arsenide is indirect, but it's not a very strongly indirect band gap. Okay. So mainly silicon and germanium are indirect band gap semiconductors. And therefore, what we see is that if you have indirect band gap materials, they are not really that good for optoelectronics. For let's say, let me not say optoelectronics, I'll say light generation and detection. Generation or detection, they are not very ideal for this. Okay. Whereas direct band gap materials are perfect for this. Okay. So ideal for lasers or LEDs and so on. Okay. These are direct band gap materials, so they are very efficient in producing light. Okay. So, and also I just want you to emphasize, I want to remember rather. So we said that refractive index is complex quantity given by N and K, right? But this is not a fixed number. Okay. We usually tend to think, refractive index of glass is 1.5. But the moment anybody says what is the refractive index, you should say at what wavelength, because they exhibit a dispersion. So this is not a fixed number. Okay. So it depends essentially. It depends on wavelength. Okay. And this we usually call as dispersion. So you should not confuse between the dispersion here. When I say dispersion, I mean in terms of materials, I mean the variation of the optical parameters with wavelength or frequency. The wave itself can have a dispersion, which is essentially the relation between the wave vector and the frequency. Okay, so depending on the context, we have to understand what we are talking. All right. So, and that's why you see that the absorption coefficient is not constant. It varies as a function of frequency. All right. So yeah, this is basically about the semiconductors, how they behave, right, qualitatively. And the last type of material that I want to talk about is metal. Okay. We are all familiar with metals. We see them everywhere, right? And they are always, shiny. If they're polished, they are very shiny. So shiny materials which basically reflect a lot of light, right? Shiny materials which reflect visible wavelengths. Okay. So why do they reflect visible wavelengths? Well, it turns out that the response of the metals is essentially because of what we call as free carriers. Okay, we are all familiar with the fact that metals have lot of free electrons, right? Metals have excess free electrons. Therefore, whenever an electromagnetic wave is incident on that, the electrons can move, and that process is what we call as free carrier response, and that essentially determines the properties of metals. And we will do that shortly. Okay, we'll go to that, but right now I just want you to understand that the difference between semiconductor and metal. In case of semiconductors, the electrons are actually bound to the nucleus. Okay, so these are bound electrons, whereas in metals the electrons are free to move about anywhere they want, and so the response because of that will be different. Okay, how different? Well, you see here the reflectivity of a metal, in this case this is silver, and reflectivity of silver as a function of wavelength. And what we see is that in most of the visible and IR wavelengths, we have nearly very high, I think about 90% or so higher, 90% reflectivity or higher. Okay, but above a certain frequency, okay, in metals we can define what is known as a plasma frequency. Okay, where up to the frequency, the cutoff frequency up to which the metals can reflect. Okay, so if your frequency omega is less than omega p, we call this as plasma frequency. Okay, you can have metals reflecting. Okay, so that's why you see that this is my edge. So this is my omega p. So I mean, okay, you have to get used to the looking at wavelength and frequency alternatively. Okay, in this case my wavelength is increasing, so my frequency is reducing. Okay, so omega is reducing in this way. So for all the frequencies less than omega p, I see my reflectivity to be high. Okay, but above that, it turns out that the metals usually are behaving more or less like a dielectric. Okay, it also is understandable because you have free electrons, but if you go to very high frequencies, the electrons do not respond very fast. Okay, and then effectively they are like a dielectric. Okay, so if you look at metals broadly, you have metals like silver or even aluminum, which are white, almost whitish in color. White because they reflect all visible wavelengths. You have other metals like gold, for example, which is yellowish in color. The reason why gold is yellow is because you have the free carrier response, and also you have what are known as interband transitions. Okay, so if you look at gold has an electronic structure in the outermost shells will be something like 5d and 6s. Okay, 5d should have 10 electrons and 6s will be, I think, 1 electron or so. So what happens is generally you have the outer shell which is contributing to conduction, but you can also have sometimes electrons excited from the inner shells, which we call as interband transitions, from the d to empty states above that. Okay, interband transitions, and because of this interband transition there can be absorption, and because of that gold has that characteristic yellow color. Okay, and even in the case of, let's say, another material like copper is greenish color. Okay, this is greenish yellow. Okay, this also is because of interband transitions. Okay, they have slight different colors. Okay, so broadly, yeah, this is how we understand the basic difference between metals and semiconductors. All right. So, any questions at this point? Okay. All right. If there are no questions, I'll just make a couple of more points and then I'll stop. All right. So, I said refractive index, complex quantity is what we can use to define materials. But in addition, you can also define, of course, permittivity. Okay? And it also turns out that you can also define it in terms of conductivity. So you have various ways of representing the optical response. Okay, you can call it refractive index, complex refractive index, which is n plus I kappa, or equivalently, you can call it complex permittivity, epsilon 1 plus I epsilon 2, or equivalently, you can call it sigma conductivity, which is complex again, sigma 1 plus I sigma 2. Okay, all of these three are complete descriptions. So any one of them you can pick, and that has the necessary information. Okay, so sometimes we use one or the other. Okay, we have already seen the relation between the refractive index and the epsilon. Okay, if you look at the Maxwell's equation and substitute in that, you will see that the complex refractive index is essentially equal to the square of that is essentially equal to the permittivity. Okay, so I mean, I can just try to derive those relations. I mean, basically n square if I take, so essentially I'll have n square minus kappa square plus 2nk will be equal to epsilon 1 plus I epsilon 2. So you can immediately see that the real part of permittivity, epsilon 1, is going to be n square minus kappa square, and the imaginary part of permittivity is going to be 2n kappa. Okay, this should be an I here. All right. So this is how we can convert between one to the other. All right. And of course, using this, you can do some basic algebra, and you will get these relations that are shown on the right here. So effectively giving you, if you are given permittivity numbers, you can always compute the refractive index. Okay. So I don't want to go through that, so I just put it on the slide already. So yeah, real and imaginary parts. Oh, by the way, the notations also can be sometimes, different, slightly different. Okay, but we understand what it means. I said N1, right? N1 is my real part of refractive index, I said. In some other cases, people use N prime. Okay, for imaginary part, I call it N2. Sometimes people call it kappa or N double prime. Okay, they're all equivalent. There's no big difference. There's no difference essentially. It's just the notation, right? So epsilon 1 is a real part. It could also be called as epsilon prime. Epsilon 2 is the imaginary part. Some people also call it as epsilon double prime. So all of them are quite interrelated. Okay. So once we know one set of numbers, we can always compute the other set. Okay. In more in the microwave and RF communities, people use conductivities instead of epsilons and refractive indices. Okay. So if you know conductivity, you can again compute the dielectric permittivity. The way we do that is the expression for epsilon in terms of conductivity is given by 1 plus sigma omega. I think this should be an I. So epsilon naught omega. Okay. What this is telling us is, if you know the conductivity, especially if you know the real part of the conductivity, that is related to the imaginary part of epsilon. Okay. If the material is very, very conductive, real part is high, then it's going to be absorbing significantly. Okay. And that's also a reason why, metals don't transmit, right? If you have a slightly, if you have a metal which is typical, let's say gold or silver, which is thicker than, let's say 100 nanometers, it's not going to transmit much. It's reflecting everything. Okay. And the imaginary part of conductivity will be related to the real part of epsilon and so on. Okay. So yeah, depending on the areas that you're looking at, you can have different ways of describing these things. All right. So yeah, we can, once you are given something, one set of numbers, you can compute the rest. All right. So this is a brief overview of the different types of responses. Let me just do a quick numerical just to expose you to some numbers. Okay. So here is a small example problem wherein complex refractive index of germanium at 400 nanometers is given by 4.14 plus I 2.21. Calculate the absorption coefficient and reflectivity. Well, absorption coefficient we already introduced. So this is the real and imaginary parts right here. So this is kappa. 4.14 is the real part. So absorption coefficient we saw was essentially 4 pi kappa by lambda. we should remember that this is the lambda. What wavelength are we talking about absorption? That's a very important thing. If I ask you what is the absorption in let's say germanium at 2 microns, okay, I think you would likely say that it's quite highly transmitting, because we know the band gap of germanium is about 0.8 eV, so that will roughly translate to about 1.5 microns or so. So above that, wavelengths it's going to transmit. Okay, so yeah, the absorption coefficient is given by this. So let me see, 4 pi into this is 2.215 divided by 400 nanometers, 10 power minus 9. Okay, and if you compute that, I just did that. So 7 into 10 power 7 meter per meter. Okay, per meter is the unit. Okay, well, I mean, does it make sense? Okay, so this is per meter, right? It seems like a large number. If you go back and look at the slide we had on materials, so you see here, so germanium is about 10 power 5 and 10 power 6. So yeah, this is centimeter inverse. So basically your absorption is going to be equal to, well, if you can talk of in meters or per meters or per centimeters, this is going to be 7 into 10 power 5 per centimeter inverse. All right. So yeah, the same metric. All right. So this is the absorption coefficient. And what is the reflectivity? Well, I didn't introduce the formula for reflectivity, but the reflection coefficient is going to be complex refractive index. Okay. If you have studied electromagnetic wave theory, this is a typical expression you will see: impedance, right? Impedance minus 1 divided by impedance plus 1 is a reflectivity. Okay. So in this case of refractive index, in the case of dielectric, it's just refractive index. So that is going to be equal to n minus 1 whole square plus kappa square divided by n plus 1 whole square plus kappa square. Well, what do you expect this number to be? Larger than 1 or lesser than 1? When you look at this expression, right? Yeah, what do we expect? Less than 1. The reason being, the numerator is always going to be smaller than the denominator. So this should be something less than 1, whatever that is, we can figure it out. Not much less than 1, something less than 1. Okay, I don't know how much it is, we can just compute, putting the numbers in. So one aspect we should also remember is this is considering bulk materials. But if you think of, let's say, a block of germanium of some thickness, okay, what will the transmission be, reflection be? Okay, so in this case, of course, we have to think of what is the exact thickness we have, the thickness, right? That is going to influence how much light is going to be transmitted. So I refer to it indirectly when I said, okay, metals which are greater than 100 nanometers, because even if you take metals which are like as thin as 10 nanometers, they're going to be transmittive. Okay, so it depends on the thickness. So in this case, the response is going to be more complex. For reflection, it is still okay. The same thing. I mean, even that is going to be modified depending on what kind of coherent light or incoherent light and so on. But if you take metal, if you have some thickness, transmission, if I'm looking at, let's say I'm going to have a wave incident on this, it is going to bend. And then it will travel in the medium. Again, it's going to bend and then travel out. Okay. So each interface, you're going to have some reflection, some transmission. Okay. So there is some, let me call it T2, and this is R2. This is T1, R1. So I can have even many more. The wave reflected here can come back again, reflect, and keep going back and forth. So we can sum up all that, and there is, it's a little, it's a simple expression, but we can use it, but we can't do it with pen and paper. You have to write a small program to calculate these things. Okay, or there's an analytic expression for this case, but yeah, more complicated scenarios, we have to write a program. All right. So yeah, we will probably do some exercise on this slightly later. All right. So yeah, this is about the broad classification of various materials. So what I'll do now is, let's take a break, and we will actually try to describe this. This is a very phenomenological description. Now we will try to give you more insight into that. How do we describe it? Okay, we'll just try to we'll introduce what is known as Lorentz oscillator, which helps you understand how this response occurs. Okay, and that will be a good, that will be an important model for almost all of optical materials. Okay. All right. I'll see you in the next lecture. Thank you very much for your attention.